Hello and welcome back to my channel. Today I'll be showing off my interpreter project that I made as part of CSE305. I've got two main files here. Main.java is acting as the driver. I give it a file path here for input and a file path for output. The interpreter function will call, it will parse this input file. It'll perform whatever computation needs to be done and write the output to the output file. So let's go ahead and get started. I'll show you how it works. In order to do that, though, I'll obviously have to write some input scripts for the interpreter to interpret. So what I can do is I can perform basic mathematical operations, and just so you know, the interpreter is stack-based, so I'll be using a push function. So I can push a value of 100, I'll push another value of 100, and I can multiply those. And what these binary mathematical operations are doing is it'll take the top two values off the stack, it'll perform the computation, and it'll push the result back. So if we multiply 100 by itself, we expect to get 10,000. So we'll have 10,000 on the stack. I'll push, let's say, 5,000 and then subtract, to which we would have 5,000. I could do maybe push 5 and then divide, so that'll be dividing 5,000 by 5, which we would get 1,000. And I could maybe, let's make it negative. So we should expect to find negative 1,000 on the stack after this computation is performed. I'll have to use a quit call so that the interpreter knows where to stop, and I can save that and we'll run it and see what we get. There's the output, but we'll look at the output file here, and you can see that we do get negative 1,000. So it looks like the mathematical stuff is working. That's all well and good. Let's try something else, maybe some Boolean values. So I'll put true on the stack twice, and we don't use the push call in this case. This was just how the problem was defined to us. If we're trying to put a Boolean value on the stack, we just enclose it with these colons. So I have true and true. I could AND those, to which I would expect to get true. I'll negate that value, or excuse me, not negate. In this case, since they're Booleans, I'd want to use not, so I'd have false. I could put another true, and I can't spell true for whatever reason. I'll put a true on the stack, so we'll have true and false, and then I'll OR those. So false and true, or false or true, you would expect to get true. So let's try that, see what we get. Awesome, we get true. So cool. Let's do something a bit more interesting, though. In addition to pushing integers and, say, strings, I can push what we call names. And these are essentially just strings without quotes, and we have the added constraint that they must start with a letter and can only contain letters and digits. But it's kind of irrelevant for this, but whatever. So push Brian, I'll push 10, and then what I can do with that is I can call this bind operation. So that's going to, well, I'll get rid of that space. What that's going to do is it's going to take this name Brian and it's going to assign to it the value 10. So now after this bind operation, wherever I reference Brian, it'll know what value I'm talking about. And the result of this bind operation, if it's successful, is simply a unit value. You'll see that in the output, just so you know what to expect. So we currently have a unit on the stack, and in the back end we have, we should have Brian bounded to the value 10. So now if I push Brian, I push Brian again, and then I multiply those, I will get the value of 100, which will be pushed back onto the stack. So on the stack now I have 100. Let me push, I don't know, 5, and I'll multiply that, so I'll change it to 500. I'll push another name, say alpha, and what I'll have to do is I'll have to call this swap so that I can ensure that the values are in the correct order for another bind, to which, like I said, I'll bind alpha to whatever's on the stack, which we expect it to be 500 right now. And then so I have Brian as 10 and I have alpha as 500. So if I push alpha and I push Brian and then I add them, we would expect to get 510 on the stack. And again, bind produces a unit, so technically we'll have unit 510. So I'll save that and we'll see if that works. And here we go. We do have the correct output. So binding is pretty useful. What we can also do is I could create scope using let end. So this is how that would work. So let's do, let end. So what this is doing now is I'm binding the value Brian to 10, but it's happening within this local scope. So by the time I exit this, Brian is no longer going to exist. So I'll simplify this script just a little bit so you can more clearly see what's happening. Just so you know, when I hit this end or keyword, it'll pop the top value of this local stack onto the global stack, which the only value that'll be there is going to be a unit from the successful bind, but that binding won't exist outside of the of this local scope. So when I try to multiply Brian by Brian, it's not going to know what I'm talking about and thus produce an error. So let's see what happens then. So yeah, you can see we do have the unit from the binding being successful. We also have our error here, and whenever we hit an error with a mathematical computation, we push the arguments back onto the stack, so we don't actually lose any data. But so you can see that we do have the error, which indicates that even though we declared Brian, it doesn't know what we're talking about. And just so you can see that Brian is actually still declared within this let end scope, I could then push Brian onto this local stack, and let's say I could negate the value, so we'll have -10. So instead of this let end producing a simple unit value onto the global stack, it'll now have -10 on the stack, so that's what will pop out onto the global stack. So again, we'll still get these errors, but instead of this unit value, we should see -10. Let's see what we get. All right, here I'll have to go. There we are. So you can see that we do have -10. So within this local scope, the interpreter does know what Brian is. However, it doesn't out here. So that's pretty interesting. So you can combine all these to make some pretty interesting programs. But what interpreter would be complete without function declarations? So what we can do is we can use the fun keyword to create functions as well. I'll name this one identity. We'll just keep it simple for now. We'll have to pass it one parameter, which we'll name x. We'll let the interpreter know where the function ends by using the funEnd keyword. And whatever happens in here, again, kind of like the let end scope, this has its own local scope. So if we want to create bindings in here, they won't exist outside the function. But for simplicity's sake, I'll simply push x onto the stack and we'll return. And again, like the let end, whatever value is on the top of the local stack within the function will be pushed to the global stack outside of the function. So I can push, say, 10. I can push the name of the function, and then I can call it. So we're calling identity 10, so we should just get 10 on our stack. So we can run it and see. So we do get 10. Also, I forgot to mention, just as bindings create unit values upon successful bindings, successful function declarations also create this unit value. So that's where that's coming from. But so you can see we do get 10, but we can make it a bit more interesting. I'll rename this function to cube, because then what I could do is I could produce the cube of a number. I'll push x twice and I'll multiply them, to which we would have x squared on the stack. I'll push one more x and multiply them again so that we have x cubed, and then we'll simply return that value. So I'll save that and see if that works. And just as I suspected, we actually get an error here. Why do we get an error? Well, it's because the interpreter doesn't know what this identity function is. We renamed this function to cube, so if we want to use it, we obviously have to call the right function. So you can see that we can't just, create functions willy-nilly and expect them to work. The interpreter is very strict with how we are declaring and calling things. So once I fix that, we should get our cube of x on the stack, which in this case, since we're using 10, we'd expect to find 1,000. So let's go ahead and run that. And there we go. We have 1,000 on the stack, followed by the unit from the successful function declaration. So I could continue on and create, more complex functions, but I think you get the idea of what's going on here. I hope you enjoyed watching the video. If you have any questions, you can leave comments, or if you would like to see the code, that is also available upon request. Either way, I appreciate you watching. I hope you have a good day.